start the recording there. Thank you very much. Ladies and gentlemen, friends from wherever you are, thank you very much for the interest here. We talk about 40 plus years in EMC and related areas. The key thing which I'm trying to bring across is lessons learned. Not only the lessons that I learned, but maybe, and I hope so, that these lessons can be useful for other people as well. So without going into details, I would like to point out this link here is answering the question, is EMI, electromagnetic interference, real? And there are over 400 well-documented cases where this can be shown from those years here, and it continues. We are way over 1,000 cases. I gave in 2001, almost 25 years ago, 24 years ago, 23 years ago, I gave a talk at a EMC IEEE conference in Montreal. Lessons learned, a similar thing. And I think it might be interesting to see what happened in between 2001 and 2024 as we are now. Next point, very briefly, the bio here. I've been in this business since quite some time, basically covering all these areas. Among others, I've been privileged to be a test house assessor and a competent body assessor, notified body assessor, which are certification agencies under these directives here. And of course, I'm dealing with EMC standards and regulations since long. Aside from that, I started as an EMC manager in R&D, research and development in industry. And then later on, got into my own activities, private test lab and certification body and R&D as well. And from here, I started being, again, an expert electromagnetic consultant in the place here near Zurich, Switzerland. Now, the talk is organized in the following way. There will be employment times and there will be self-employment times. And the first question is, first need for professional EMC, when did this occur? It did occur during my PhD work. I did gaseous discharge physics, and I had to use a very powerful and very much interfering 15 mega electron linear accelerator to ionize my gas with pulses, and that caused a lot of interference. Later on, I started a job in Switzerland in the research center. You see the years over here, and there we talk about EMC and NEMP. NEMP stands for nuclear electromagnetic pulse. So we talk about balanced protection. This is lightning protection, this is tempest and EMC, etc. So all these electromagnetic whatever. Then, of course, I had to dive very deep into this exoatmospheric nuclear electromagnetic pulse with simulations and testing and so on. The goal was to harden equipment, this type of thing, make it immune, so to speak. And then we had to build a system because we didn't get the big money that we wanted. So we had to invent something, which was the GTEM cell. And remember, those days were the days of Cold War. And at a certain time, the Cold War was over. Then my company changed the policy. And this military aspect, which was very strong in the beginning, in this year here, became almost eliminated, not to say completely eliminated. That was a forced transformation, consequently, into commercial EMC. And we added to this GTEM cell, which is a TEM waveguide, if you wish, the radiated emission possibilities. And we published that at this conference. This was the scientific breakthrough. And I organized, on the other hand, because this was a large company, more than 100,000 people worldwide, EMC management, awareness, training, and seminars. And then I was the appointed manager for ABB EMI Control Center, which was kind of an advisory group, so to speak. And I did do for this invention here, the GTEM cell, the international license technology transfer to the various countries. And that gave me a very, very good insight into all the patent things and the commercial aspects there. Finally, then there was the self-employment. And I started as a EMC private consultant, 1991, in Switzerland, partnering with the UK with a guy I knew from my previous work. And then I was approved as international auditor, technical as well as management systems in EMC, radio, and automotive. And then I started founding and running a company very close to Berlin, south of Berlin, in Teltow, the former German Democratic Republic, in these years. And there it was an R&D, a research and development. It was a test house, and it was a competent body. Nowadays, you would call it a notified body. But you have to consider, and this is what I'm going to talk about, the former East German area after the reunification of Germany was very, very special. We invented something here, the GTEM cell, which was an add-on, later on follow of the GTEM cell. And finally, I talk about markets and changes on the problems we experienced in the Berlin area. And later on, I report on the focus of consulting again. And finally, there's a lesson learned summary. The PhD work, that's the first part, and the reason why I got introduced into this field, basically originates from this huge X-ray machine, megawatts pulse power, and a small nanosecond pulse coming out here. And this is a setup where you basically have a test chamber where you are interested in investigate early onset of electrical discharges in compressed electronegative and insulation gases, which are used in high voltage and energy distribution systems. So this was fundamental work, and the problem was I couldn't get rid of the interference, and I had a very good PhD supervisor and a boss. I said, listen, Diethard, you're going to go to the International EMC Symposium 1981. And boy, there I learned, oh, I needed to learn, and I finally did learn how to fix a complex EMC system systematically. And EMC is not black magic. That was very important. These are patents and publications during that time. And we got the job in Switzerland now. This was the time when it started. And we were dealing with something which was EMC on the one hand side, electromagnetic compatibility, but then very strongly NEMP, nuclear electromagnetic pulse. And for simulating that, you need, for example, such an infrastructure with a generator here, pulse generator, maybe 10 megavolts or something, resistively attenuated over here, kind of a broadband dipole. And then you could test and simulate the effect onto a locomotive, which was actually live, overhead line here. And you could see how does such a very rapid radio pulse, nanoseconds, interacts and possibly negatively interacts with such a machine. Of course, in those days, there was not that much electronics inside. And in order for smaller objects, and we needed something in the lab to do experiments, we created this GTEM cell. And in that respect, I learned, because I was very active in standards, that standards are extremely conservative. Standards are resistive in the way that they will not easily take on new ideas. And one of the basic ideas was the GTEM cell is based on, emission-wise, total radiated power, while the open area test site is not taking this concept, so only taking a fraction, a geometrical fraction out of it. And okay, when you start a new job, I had an excellent job then, I was very well supported, and they sent me finally to an international training. And at that time was Dunn White Consultants, which was the big guy, very expensive, and I spent a week in London. But what I thought is kind of missing there was the why is all this happening and what is the underlying physics? That was not really well transmitted there. Okay, finally, I was a researcher, and more I got into managerial tasks. So we talk first of all about the balanced EMI protection, which is NEMP, electrostatic discharge, lightning, electromagnetic interference, radiation hazards, which is rather related to human interaction of the electromagnetic fields, and tempest. You can also call it secured communications. So at that time, the overall principle for all these things is the so-called zoning protection principle. That means you subdivide a sensitive system into blocks and make sure that from one block to the other, the transfer of energy and the EMI effects are controlled. And that is a modular approach, if you wish. This is true for emission and immunity, and is still equally true for everything electromagnetic nowadays. Military and commercial markets are totally different because the number of customers in military markets are very, very limited. And in the commercial market, it's totally different marketing and action. New technologies always drive till the very day what's needed in EMC. And good management in a corporation is very difficult to do. Imagine this was years ago, and still in smaller companies, it's still very difficult to establish. Consequently, EMC education was underdeveloped, and I had to help to improve that. And finally, I had to go through all the standards. IEC and CISPA was starting in the 1930s. Then the US military standard was in this year, and the German high frequency law was in this year. And then finally the FCC in the early 80s, late 70s, early 80s, established a regulation on emissions, basically by computers, digital devices. And finally, in this year, the EU came up with what we call now as the EMC directive. The landscape there was very limited EU commercial EMC research and a relatively small EU EMC job market. I'm not talking about the military side, I'm talking about the commercial side. And then finally I said to myself, well, wow, maybe this new EMC directive is going to be a game changer. And since the company, thought about selling off these activities, ABB outsourcing, selling own EMC activities and services, I thought, maybe is there any future, any fun for me in this present corporate situation? You have to understand, in 88, management changed, and Brown Boveri got together with ASEA and formed ABB, and everything was changed. In the beginning, we were one research center. All of a sudden, we were 5, 6, or 7, or whatever. And these are the publication and the links that originated during that time. Starting as a private consultant, so the answer was for me, yes, I'll take the risk. I go out on my own. This is a risky step. Of course, freedom is there. Entrepreneurship, marketing, contracts, no more steady income. But everybody will understand Rome was not built in one day. So yes, can do this if You have a solid plan, a solid plan B. You have an essential personal business insurance established because you need to think about those things. And I tell you, surprises are guaranteed always. Then you have to outsource services like tax and legal and other things which are not your core business. You have to learn guerrilla marketing. Your time, your budget is very limited and cannot be compared to a major corporation. You're a one-man show. And don't underestimate the cost for continued education, going to symposia, going through management courses. You need to learn all this stuff, which goes way above a manager in a company. You're now out on your own. You're the CEO, basically. And you need to find your market niche and answer the question, what is fun to you? What is profitable? And of course, you have to think about contract risk management. Most importantly, you have to keep the work-life balance. And you should avoid inappropriate contacts. And that means saying no is often very hard to do. You should have, in order to be more or less independent, a financial reserve covering at least 1 year without any income. Aside from that, you need passion. Curiosity is driving you. I'm an R&D guy. A clear perspective. You need self-confidence. You need flexibility. And you need endurance. It's like a marathon. Okay, so very nice thing was I was given the chance to be approved as an international auditor in these fields here. And that was challenging, but also financially rewarding. And these were the areas: test labs and certification, test labs and calibration labs assessment, and product certification bodies needed to be assessed. And basically over the years, I did commercial labs, military labs in all these areas. I had 400 plus labs and certification bodies in Europe, in the United States, and in Asia. It helps greatly the assessment process on the quality, knowing the two sides of the desk. I've been sitting on the other side, and now I was an assessor, so I could understand the situation much better than somebody else. And you assess based on standards, regulation, and technical competence. And there are imperfection in the standards. You need to understand that. And consequently, at the end of the day, when we take CE and the notified body assessment issues, I also assess those bodies, you are assessing against the essential, that means protection requirements of that particular CE directive. So that means in an EMC world, you should not be interfered from outside in an inappropriate way, or you should emit not above a certain level. And that details, all the details are defined in standards, and that's sometimes a jungle to look into. Then you are employed as a freelancer expert by government organizations, and you need a regular training as an auditor, typically annually. And in the beginning, this business was international, but more and more time going on, it became a national thing because those companies in Asia and so they trained their own people and they were capable of speaking the national language, the local language, which was a big, big bonus. And of course, I don't speak Mandarin, Chinese, so sorry, folks, nor do I speak Japanese. Finally, I started founding a company after this EMC consultancy, basically in Switzerland and the UK. And this was near Berlin Teltow. This is south of Berlin in the Berlin-Brandenburg area, the former German Democratic Republic area, German Democratic Republic. So basically, this is now high risk business, high investment cost. And what partner do you have? You're a one-man show, and now you need to find partners. Difficult process. You have to consider the political and business scene, which was tricky. Think of reunification. There were lots of things going on. Treuhand Anstalt, and which is a trust agency, if you wish, a government selling off the state-owned companies, and there was a lot of hickhack going on. To the very point, there were some assassinations going on. It was kind of not Wild West, it was a Wild East situation. The situation arises now. You need to recruit qualified staff, and that's not so easy. And you need a core staff. So basically a test house CEO and a research and development CEO. And we started at a friend's place and then finally developed a business plan and said, okay, we need bank loans. You were always personally financially liable, GmbH, limited or not, irrelevant, you were liable. And unfortunately, in those days, there was the dot-com bubble and the internet hype, and venture capital was not available to EMC. That was difficult. So you have to do a market analysis, standalone criteria, not a Me Too thing, and then do all the due relevant things. And we finally became an accredited test house and an accredited, today you would call it notified body. And we did research and development, and here are the publications again. And we did some seminars, etc. We invented the GTEM cell. I'll get to that in a minute. And we had a pretty crazy good situation from 1986 to 88, because in 1986, very late, the Brussels directive was transposed into German law. And in the years before, it was very hard. And then there was the gold rush. We made money like hell, but only a certain limited time, because new risks and trends came up. There was a strong political impact, dramatic changes, serious problem, and finally the company came to an end. So let me be systematic and go through the research. We created a smaller and a bigger cell where you put the object under test here, and then you are using it for emission or immunity, mainly for immunity here. And the bonus is you don't have to rotate the object under test through the field as you have to do it in a GTEM cell, but you switch polarity of these transmission lines. Okay, and small, medium-sized enterprises, well, this is another thing to learn. We had patents, but these patents are critical and problematic. They cost a lot of money. And if you want to defend those patents, you needed a lot of money, 300,000 Deutschmarks in those days. And a small company doesn't have that. So you have the patent, but somebody can basically steal it from you and will get away with it. If you're a large corporation, that will not happen. On the other hand, the EMC Standard Committee, and I was very, very active also the years before in IEEE, in Senelec. I was in German Defense Standards and American National Institute of Standards. We created absorber standards in the time when we created the GTEM cell. And in those days, absorbers were kind of, how shall I put it, black magic. And we started shining some light in it by doing proper research, and then created a standard with other people. And that standard still exists, and this will be continued. And that time it was 5 gigahertz. Boy, that was high. Today you go up to 100 gigahertz and what have you. Okay, so Global market product marketing will cost you a lot of money, and it is several times the investment cost for R&D. And how do you finance that? Corporation, yes, okay. But what partner? Are they honest? Do you want a license? Can you defend that license? Etc., etc. All problematic areas. Official bureaucratic funding was a key problem in those times. There was government funding on the one hand side, but it was inappropriate in a way that the market sets the pace and not the government. So we had big, big problems. We did get money, but okay. Now, running and auditing EMC test labs teaches you certain risk and real world EMC. And that is always, if you do EMC early, you save cost. If you do it late when it's installed outside in the field, you pay dearly or the cost is simply exploding. That's an old and wise story and hasn't changed yet. Often, severe client EMC management problems do occur in very critical things like functional safety issues, etc. And you always start testing with disturbance because that does not kill the equipment. And then you go to the later and more dangerous things like immunity tests. A basic rule is, and there's also something learned, 60% mostly conducted problems. The next one above here is then starting to get more into fields. It's a slow transition. That's physics. And absorber chambers have a problem typically in this range. Why? They are shielded resonance and local cavity resonances. Low frequency, you have degraded absorber performance, and the equipment under test is going to introduce cable resonances. A quarter wavelengths here is a typical case. They're grounded on one side, and then they are kind of a monopole antenna. So the next thing is, when you deal with all these standards, you learn pretty soon there are lots of imperfections. And these imperfections are, for example, in the case of a ground plane and you're doing an emission test, you do a height scan here. This is the object under test. The question is, what do you measure up here? Nothing. It is not foreseen in the standard unless you do, as in a reverberation chamber, a GTEM cell, total radiator power. You don't do that. You're measuring a segment. Moreover, what happens if you are installing such an equipment, well tested, 100% okay, in a tall rising building? The standard is irrelevant. And another tricky situation arises if you have harmonized standards in this field here. They only give the presumption of conformity, not a guarantee. If you want the guarantee, you need to go to a notified body and they do an assessment against the essential requirements. You can also say it's kind of insurance policy, which sometimes is very wise to take. So in other words, there are problems, and let's look at what is causing the problem. Causing the problem is, in an emission test, the fact that EMC is strongly believing into putting a ground plane, which in the first place is pretty much, excuse me the word, idiotic. No telecommunication engineer would do that. A person would do a fully anechoic chamber test. But when you put this has a reason. When they started in the 30s, they did it on a parking lot. And when a parking lot was wet or icy or snowy or whatever, they had different reflections here and they didn't get anywhere. Said, okay, let's put a metallic ground plane here. Fine. Then later on, if you do that, you have two signals, direct signal and an indirect signal, and you need to scan for the maximum of your emission. And there's certain parts up here which you never capture because you stop at about 4 meters, if it is 3 meter distance or 10 meter distance. And if you look at it very clearly, then of course you're going through this kind of a pattern here. So that changes the antenna factors and all these things, and that change is strong in the low frequency range and not so strong in the higher frequency range, because the coupling, this is now image theory to the part down here, is of course stronger the lower you get here and the lower the frequency is. So this is mutual coupling unwanted. This is where you can read it. This is an old story, but still valid, and all the ETSU standards you can download for free, by the way. Okay, another thing is you run these labs and you find other imperfections, near field, far field, and the question is, how far is far, and is far enough? You go through Maxwell theory, blah, 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 pointing vector, all this kind of stuff is crystal clear from a theory point of view. And then you look at the literature, find all these things and say, yeah, this is the transition from a reactive field into a plane wave. And you start asking the question, what does apply for me in EMC? Well, EMC mostly is not as precise as some other sciences are because you have so many quantities involved. And the key factor is, what is it that you accept as a uncertainty? Is it a 1 dB? Okay. And then basically you can say it depends also on the size of the object. D, for example, would be the test object of the antenna. So, and if you have another issue that is very much focusing antenna, that means high gain antennas, which do strong beam forming, then you have to go very far away in order to reach really the radiation pattern in free space. Otherwise, you have problems. And exactly this is the issue in most of the EMC chambers, where you measure at 3 meter or 10 meter. That distance related to the wavelengths is basically not enough to say we are in free space. We are far enough away. So this is another compromise you need to understand. If you are in free space, well, it's clear cut. It's Ohm's law in free space, you know, the voltage divided by the current is the resistance. And here it's a special impedance, 377 ohm or 120 pi ohm. E, the E field over the H field, and here you go. But there are transitional zones. Another thing which is mind-blowing is the convention. You can say, well, it's a convention. People agreed on it. You have a magnetic loop, 60 centimeters, shielded. It will be used typically 9 kilohertz to 30 megahertz on a 50 kilohertz to 30 megahertz, 3 meter distance. Magnetic loop, vertically oriented. And then they say, oh, we convert E over H with 51.5 dB. And you start wondering, where did that come from? Well, here's the answer. That's 20 the logarithm of 377 ohms. And boy, I mean, it goes without saying, in this frequency range, you never, ever, in this distance, are in far field. You have to know it's a convention, like it or not. So the question is, what does that test tell you in terms of physics, where you try to answer the problem or the question, is my equipment fit for a certain application? And you have tested in an artificial environment, which is not necessarily representative. That's a risk. Now, when you go through physics, you have, these are the well-known places here. I took a lecture. You can also find this in the textbooks, Rayleigh, Fresnel, and Fraunhofer. And over here, do we really have a nearly planar phase wavefront? So in the beginning, it's kind of a spherical wave, and then as you step away, it's almost getting planar. And the question is, how accurate is it? If you say, well, it's about 1 dB, okay, yes, you then declare this as far field. And as I said, in some cases where you have microwave, let's say 30, maybe 40 dB gain antennas, well, you need to go very far away till you really see the main lobe and the side lobes and everything. Okay, so EMC is really a compromise. Next part here, another compromise is an open air test site with the ground plane is useless today. Why? Because of the always everywhere almost existing radio background noise. This is a classical function here, which the ITU puts out and says this is frequency. This is 30 megahertz. We're measuring in this range, but below we measure here. And there you see a number of curves, which basically represent more or less perturbed areas. It is clear that a rural area is normally having less emissions, an industrial area having a lot of emissions. However, if you go through all the things here, which ITU in Geneva puts out, you start asking the question, how valid is that as a general description? You start asking the question, are the measurement procedures that they apply for measuring these frequency, for example, below 30 megahertz, really the one that should be used? They go and put up a small monopole with ground plane over just ordinary soil and measure at the bottom. Now, antennas are typically not mounted at the bottom, but somewhere higher on the roof. And of course, the question arises, is that directly related? The answer is no. It is probably more interference up on the roof than on the ground. So some areas we could say, well, they are 20 to 30 dB underestimated. But this is a lot of research going on now, and I think in pretty soon, pretty short time, we will have more information. So in other words, the data set that this is built on seems to be not, let's put it mildly, not optimal, right? Therefore, if you take these natural background noise levels as minimum risk or minimum level for radiant emission, then the whole exercise becomes questionable. But thanks God, CISPR Age, they are working on finding new and better methods, scenarios, and do incorporate the cumulation. I mean, if you have many sources in an area, how should they be added? You cannot add them linearly. They're typically not in phase, etc., etc. All these questions do arise and are very, very important. Now, let me continue with the activity here in Switzerland. What I want to say is basically the story in Berlin ended in a peculiar situation in the way that we had major difficulties fighting the political system there. We did not understand in those days that the Stasi and the National Volksarmy, etc., and all the people that basically spent their life in the German Democratic Republic for the past 30, 40 years, of course, had their connections. And when it came to government funding, well, let me say it bluntly, that innocent guy from the West was left out. Well, I learned it the hard way, but okay. So that was the situation as it was around 2000. And again, internet was the big hype, and that bubble bursted later on. So, but venture capital was not available. So here we go. EMC market activities in those days and today are increasing. It goes without saying that EMC is getting more and more important. And on the other hand, why didn't you publish such a lot? Well, I publish a lot here, but in these times I had to sign non-disclosure agreement with clients. And that basically takes the chance to publish more or less away. EMC research and development taking off lately by coordinated, well-coordinated EU funding, and that makes me very hopeful. All these PhD projects funded by the EU, that's a step in the right direction. Sad to say that some of the university chair positions, Professor Emeritus, disappear or disappeared in Germany and the UK. That is not a good idea and still proves that the importance of CMC is not fully recognized there. Then, going back here into the times when we are talking about the Swiss referendum, I'm jumping back now. They decided here, no, we will not join the economic area, the European Economic Area. So that was one of the driving factors because I said, well, I need to go and start my company in Germany, Intel. About 10 years later, they finally signed a memorandum, a mutual recognition agreement with the EU. So nowadays, basically the same standards and same regulations apply in Switzerland as in the rest of Europe. And then here we had the EMC directive. As I told you, was very, very lightly transposed into German law. And that was a serious political lay by the German reunification, which made our life very hard before the gold rush appeared in those years from 1996 to 1998. Okay, recently the number of contributions, good contributions, for example, IEEE transactions on EMC, is increasing from Far East. Do not underestimate that. They have done their homework and they are catching up. Markets only indirectly are driven by government regulations. The key thing that is driving it is EMC awareness in the companies, and that is also for importers. Market surveillance, German Federal Network Agency, Bundesnetzagentur, is doing an excellent job, and that's very important, but they can only do a certain amount of testing, and they have a smart way to assess millions of products on the internet, but they only indirectly help with the EMC problem solution. Governments do spot checks, there's jurisdiction, the executive files, etc., etc., etc. And finally, competitors' action are critical. Let me come to the summary of lessons learned. And that is to say, would I choose EMC again? Yes, I'm an optimist, but I would try to avoid mistakes I made in the past and lessons I learned. The driving technologies are mobile telecommunications. And on the other hand, we're getting lower in frequency because of power grid issues. And we are expanding to the upper frequency range and into the lower frequency range. I mentioned already this, that the government is not your marketing agency, that you can take for granted. After the German reunification, the old boys network, German Democratic Republic, SED, the party, Stasi network, were still dominating that scene. And that was critical. So we didn't get the funding and other people did. Introduction of new technologies is always driving things, but there's a delay between that and the standards by maybe 3 to 5 years. Setting up a private EMC test center is high risk business and needs to be planned like a factory, a production. EMC awareness around 2000 was low and still today is underdeveloped in small, medium-sized enterprises. Believe me, that's a given fact. The big companies, I think they're mostly doing quite well, but the small ones are still suffering. Today, more than ever, expert staffing is very critical. That's a situation which is positive for you, possibly going into this field, because there is now a chance to get a job. And given that you managed to get the work-life balance correctly, then this is an interesting one. On the other hand, company EMC mostly problematic. Their deficiencies. If there is no EMC mentor when you got the job, then it is critical for on-the-job EMC training. If you have an R&D, a research and development boss, saying, just do your job, and his attitude is to say, well, just do your job, is EMC now an attractive job or burden? You need to make sure you're not getting the mental and consequently a body burnout. So that's critical, but that's true for many areas. In times of recession, many times EMC is postponed or simply canceled, or we take the approach, oh, we hope for the best, and so on and so forth. When the house is on fire, EMC has seriously gone wrong. Then all of a sudden, mostly EMC doesn't matter anymore. Consultant, please help us immediately. Well, it's problematic. I showed you the curve. If you do it early, it's okay. If you do it late, your chances are not so high anymore. Finally, we get to this point here, which is a very busy slide. This is a repeat, and standards are compromises in many ways: technical, physics, practicality, economy, quick emerging technologies, industrial lobbying and the standards, etc., etc. The guys defending the spectrum are not so strong anymore, unfortunately. And EMC standards slowly improving. The key question is the apparatus, the system, the installation fit for reliable use with functioning as intended? So there are now better harmonization of standards. There are alternative test methods. Open air test site is the open field, as I told you. Why are absorber chambers validated for radiated disturbances, so to speak, emission in a 3D fashion over the turntable, and for immunity a 2D? Nobody can explain that in terms of physics. I think we need to rethink that. There are more realistic disturbance immunity scenarios now, in particular when it comes to multiple sources that will add up in high quantities. What's the EMI, the electromagnetic interference probability? Many issues are related to calibration. Instrument versus compliance measurement uncertainty is an issue, because right now we're only looking at the instrument and not the interaction between the EUT and your setup. And what happens if you try to find large system compliance? We're talking about wind turbines, photovoltaic units, etc., etc. Automotive charging. Here we need sensors, drones, because we have a radiation pattern which is in 3D. And below 30 megahertz, we need to fly across the whole thing and take the pattern. That is not, to my knowledge, done anywhere right now. Computer codes, of course, they are very important. They improved over the many years to a very high level, but still, there is the need for EMC engineering and do a risk assessment. Only partial testing is possible. The more complex your system will get, for example, autonomous driving. There are other issues like classical EMI receivers versus FFT receivers. There's a risk of overloading them, etc., etc. Just keep that in mind. Line stabilization networks, you say, well, that's conductive thing. That's pretty straightforward and clear. Well, these standards define you do not have to specify the phase. And guess what? As a result, and this is very latest research being done in the European Union from high-level people, measurement uncertainty in some cases of extreme sources, low, high, could be 40 dB. Wow. Typically, you would say that's 3 dB or something in that order, plus minus. Important improvements were triggered by the FDA, the Federal Drug Administration in the US, medical standards. They do the risk assessment and they measure in time and frequency domain, all these things. Number 11 here is still technical imperfection do exist in the standards today. We want to eliminate these severe ambiguities. And all this has legal consequences. So that is critical. But I'm hopeful because EU is waking up, Brussels, and they do proper funding and these positions and they do R&D studies, but they need to catch up because we have a lot of things to do not to get into a situation where the standards are physics nonsense and we have a legal problem. This cannot happen. So the next step is governments need to understand the overall importance of EMC product compliance, global markets, and fair trade. The guy who puts money into EMC and the other person not, well, that's unfair trade. And finally, we all shall better protect all frequency spectrum or spectra because of the importance partially sensitive radio communication signal noise ratio issue. If not done, this leads to continued dramatic, irresponsible, irrevocable electromagnetic environmental pollution of our planet. Finally, let me say thank you very much, but it's not finished yet. Here's the breaking news. Free of charge standard access. The companies, for example, for not ETSI standard, the telecommunication standard, but all the other standards have to pay dearly. This could be tens of thousands of euro, and that for a small company is very difficult. Now, the European Court of Justice has ruled that there is probably, we need to wait, the order that this has to be free access because any legal text must be given to the citizens for free. So, and therefore I would like to conclude and turn it back. Sebastian, go ahead, please.